Good afternoon to everyone. I am Virendra Sharma from Bhabha Atomic Research Center, a member of Indian National Young Academy of Science. Today, on behalf of Indian National Young Academy of Science and Indian National Science Academy Mumbai chapter, I welcome to everyone to talk number 8 of weekend webinar series on windows of opportunities in science and engineering, organized by Indian National Science Young Academy of Science, INIAS, and Indian National Science Academy, INSA. The details of INIAS and INSA can be found on the following website link. It is all things the work done by the INIAS and their activity can be all available on the INIAS YouTube. So this is the talk number 8. Till now we started this activity in the first week of April, and the talk number 1 was on the 3rd April on the higher education opportunity after BE BTech by Dr. Arpita Mandal from IIT Bombay. Then after we had a talk on 10th April, the S in STM, Relevance and Opportunity by Dr. Jhanvi Punekar from IIT Mumbai. Then we had on Roadmap to Stress-Free Research Journey by Dr. Tuli Bakshi from IIT Bombay. Then Basic Science to Pursue or Not to by Dr. Sandeep Rugare from UGC DE CSR Kolkata. On 1st May, we had Sustainability, What We Need versus What We Think We Need by Dr. Alovikita Agarwal from IIT Roorkee. On 15th May, we had Radiation Physics, Opportunity in Medical Sciences by Mr. Shrikant Kale from Tata Memorial Hospital, Mumbai. And the last week, we had Contributing to Research Policy and Practice through Science Education Career by Deepa Cherry from Homi Bhabha Center for Science Education in Mumbai. If you have missed these talks, they are all available on INIAS YouTube. Just look into playlist by Windows of Opportunity. So I'm honored to introduce today's speaker, the talk number 8, Dr. Anup Mahajan from Indian Institute of Tropical Meteorology, Pune. He is also a INIAS member. And about the brief about the Dr. Mahajan, he did his PhD from School of Chemistry, University Leeds, UK, under supervision by Professor John M.C. Plain. Then after he did postdoc from 2000 up till 2012 in Laboratory for Atmospheric and Climate Science in Spain. And after that, he has joined as a scientist position at Indian Institute of Tropical Meteorology, Pune. He has received several awards and honors. I have highlighted 2 awards. He has received the National Academy of Science India Scopus Young Scientist Award in 2019, and he is a member of Indian National Young Academy of Science from 2020 to 2024. With this brief introduction, now I again invite Dr. Anup Mahajan for his talk. Dr. Mahajan,
thank you, sir.
Over to you.
Thank you, Virendra. That's a very kind introduction. So I'm going to try and share my screen. Just a disclaimer that my internet is not very strong right now because we don't have any electricity. So hopefully we'll not have any hiccups. But if that happens, I'll try and log back in as soon as possible. But having said that, I'm going to share my screen and I'll stop my video. So let's bandwidth. Virendra, can you stop sharing your screen so I can share mine here? Great, thank you. Okay, right, so let me jump to the very first slide itself and go into full screen mode, and also let me just stop my video. Okay, all right, sorry. Yeah, here we are. Okay, so today I'm going to be talking about climate sciences and basically talking about like a few opportunities that we have for doing multidisciplinary science and research in climate sciences. And it's obviously a very broad talk and fairly superficial, but hopefully this gives you a good idea of how and who can contribute towards climate sciences. So to start off with something very simple as to why do we need to study climate sciences? Uh, okay, yeah. So let's start with defining what is climate sciences, no? Because people get muddled up between climate and weather. That's a usual confusion that most people tend to have. A simple way to think about it is the quote on the bottom, which says that weather refers to short-term changes in the atmosphere. So if it is raining today, that's mainly weather. It's very warm today. It's mainly weather related. And climate describes what the weather is like over long periods of time over a specific area. So if we say, what is the expected rainfall in Pune as compared to expected rainfall in Delhi, these are long-term trends and they will be determined by your climate rather than saying that by weather. So weather is going to talk about day-to-day changes, but long-term changes is what we are trying to understand by studying climate sciences. And climate science is the study of relatively long-term weather conditions, typically spanning decades to centuries. So we're talking about pretty long-term rather than just year-to-year variations. We're talking about decadal variations mostly, and of course beyond. And we also go to geological timescales. For example, we know during the Jurassic period, the Earth was warmer than it is now. So that is also, that was the climate during the Jurassic period. So that's basically what we try and understand. And through this, we also try and understand what's going to happen in the future and how things are going to change. So why are we worried about this? Mainly because we've seen lots of proxies talking about how the climate is changing, how the temperatures are increasing, how precipitation is changing, etc., etc. And the drivers of this are basically greenhouse gases. Greenhouse gases are, I'm sure all of you have heard about carbon dioxide, etc. So they're mainly anthropogenic emissions right now. There is a strong natural cycle also, but it has been petered, so basically changed because of anthropogenic emissions. And it's not just fossil fuel burning, but the impact of fossil fuel burning on the climate, which has secondary impacts such as changing, the thawing of the permafrost, which is like the frozen region in the Arctic. So that changes the amount of emissions coming out from that ground. Or, for example, agricultural changes that we are making, that also leads to changes in these greenhouse gases. So what's happening is, because of all these different type of sources that you see over here, what is happening is we have basically started increasing the levels of these greenhouse gases in the atmosphere. As I said, the most common one is carbon dioxide. And the reason why that matters is basically it leads to global warming. So global warming is basically the driver of climate change. Global warming is the Earth is getting warm, and the manifestations of this change in temperature turn out to be in terms of changes in precipitation, for example, or changes in the hydrological cycle, etc. And that's called climate change. But in terms of global warming, I'm sure all of you know about this, but just a quick review. So what happens is we have solar radiation coming onto the Earth from the sun, and this is pretty constant. It does change, but over very time scales as compared to what we are seeing in terms of temperature changes. So in theory, you can hold it as near constant for a very short time scale. And what happens is the light waves come and pass through the atmosphere, and most of this radiation is absorbed by the Earth, because basically that's where it comes and hits the surface. And because of that, the Earth warms up. Now, because the Earth's temperature is very low as compared to the sun, most of our radiation goes out in the form of infrared radiation. So these waves escape back into space. That's basically what cools the Earth, right? So there's a balance between the incoming radiation and the outgoing radiation. Now, what greenhouse gases do is they basically act as a blanket on the Earth. So basically what they're going to do is they're going to reduce the outgoing radiation. So basically this outgoing radiation gets trapped in the atmosphere, and that leads to a change in the temperature. And to think about it, it's a very simple model. I use this analogy all the time in my talks and in my lectures, and it's the simplest form of trying to compute global warming or temperature changes is thinking about a bucket. In a bucket, you have some water coming in and some water going out. Now, this is as simple as it can get. What greenhouse gases essentially do is they reduce the outflow. So because of these greenhouse gases, the amount of radiation going out reduces. And because the inflow hasn't changed, the total concentration of X in the box, which in our case is temperature, is going to increase. And this is as simple as it can get. Unfortunately, things are not as simple as that, right? Otherwise, we would not need to study this very much in detail. But the reason we have to is because there's a lot of complex processes that happen within the box. And in our case, the box is the planet, right? So there's an interaction of several different kinds, and that is what we are trying to understand as climate scientists. And for this, obviously, as you can imagine, you can't just have one single type of science. You need to have a lot of different types of sciences, because this is a statistic from the IPCC, which is the Intergovernmental Panel for Climate Change. And they're talking about some of the processes which control the concentration of these greenhouse gases in the atmosphere and what kind of changes they can cause. So basically what you can see is it's not a static system, it's extremely dynamic, and pretty much everything is interacting with each other. So for example, the hydrosphere, that is the oceans, etc., are interacting with the ice, are interacting with the atmosphere. There's a lot of exchange of heat, wind, and even about of particles and aerosols, etc. From the land, we know we are emitting lots of greenhouse gases, but in addition to that, we have biogenic emissions. So for example, the plants emit things. What kind of impacts do they have on the atmosphere? Then we have, very episodic events like volcanoes, etc. They also end up affecting the climate. So what we do as climate scientists is we are trying to get a hold on each of these processes. And as you can see, it's a vast collection of processes. And they're not just physical processes in terms of heat exchanges, but we also have mass exchange. So we need people who understand the chemistry of these things, or what kind of impacts it can have. We obviously need physicists so that we can understand what kind of radiation changes are occurring. We need biologists because the biosphere ends up having a huge impact on the atmosphere itself. So what we are talking about is we are basically talking about the three basic sciences which have to be accounted for if we are going to get our projections correct. So physics, chemistry, and biology are there. But within that, even we have subgroups. For example, if we are talking about, say, the ocean and atmosphere exchange, then we are also talking about how the sea ice changes. So we get in some glaciologists. If we are talking about changes because of aerosols, etc., we need people who can understand how these aerosols can scatter or absorb, etc. So we need a lot of people with expertise to be able to solve this entire system and be able to predict what's going to happen in the future. So how do we go about doing that? The basic point, as I said, is it's a very large issue. So it's not as simple as getting a bunch of scientists from a single field in a room and getting them to talk, but we actually need people who speak very different languages, because as we all know, biologists speak a slightly different language to physicists and chemists. So we need all these people to interact with each other and come and solve this issue. So what we do is, basically what happens is climate change is a large issue. Majority of the sciences and engineering disciplines are involved. And on top of this, away from the basic sciences, we also have social sciences, because the effects of climate change are on people. So obviously we need anthropologists and social scientists who are also involved, because finally the stakeholders are the people itself. The businesses and industries also have a stake. So we need economists. We need to try and understand what kind of impacts will climate change have on the economy of the future. So we need people from that field also to be involved in climate sciences. So it involves citizens, politicians, public policy experts, and advocates. Every sector of the economy is affected. Basically all aspects of our lives are touched. So we're talking about the environment, jobs, health, politics, national security, arts, religion, etc. So basically the point over here is this is probably the one true multidisciplinary science that is prevalent in the world right now, because we have pretty much everybody affected because of climate sciences. And so how do we start, getting this information together, right? So climate sciences broadly can be split up into three different parts. The first one is descriptive climatology. The second one is scientific climatology. And the third one is applied climatology. So what are the definitions of this? The descriptive climatology describes the climates of the world. It deals with the observed geographic or temporal distribution of meteorological observations over a specified period of time. So basically, what descriptive climatology does is answers the question, what is happening in the world, right? So this would usually involve going and making observations in different parts of the world to try and understand what changes are occurring. So for example, there are people who go down to the Antarctic and measure the ice sheets over there. That is to answer the question, what is happening to the ice sheets right now? Are they increasing? Are they decreasing? So basically just trying to get the ground truthing of it. Another simple thing is if you want to understand how precipitation is changing over India, the first step you need to do is go and make observations of rainfall all over the country. So making observations of rainfall is again contributing to descriptive climatology and is helping answer the question, what? The second one is scientific climatology. Now, this addresses the nature and controls of the Earth's climate and the causes of climate variability and changes on all time scales. So basically, this is now getting into processes, right? So we are trying to understand, after the first step, we have our observations. Now we are trying to understand what are the drivers of these observations? What are the processes that are controlling these observations? What is the real science behind these observations? Because unless we understand what is happening, we will not be able to.
It seems there is some internet problem from the speaker side. So we are trying to call him. Just wait for a few minutes.
Sorry about that. I had lost connection. Can I continue or?
Yes, please.
Okay. Yeah, sorry about that. As I said, I'm on very poor internet. I'll put off my video and share my screen. I'm not sure until where you guys heard, but I'm assuming it was until the descriptive climatology. But yeah, so basically the point where I stopped was there are three broad topics within climate sciences, and in those three topics, there is descriptive climatology, scientific climatology, and applied climatology. The descriptive climatology describes the climates of the world, as I said, and it is answering the question what. Whereas scientific climatology is talking about the processes, right? So this is where I think I cut off. So basically what we are trying to do is understand the processes and be able to compute what's going to happen. As in, are we able to compute the way the first part, that is the descriptive climatology, sees things? Because once we are able to compute that, then we have confidence in our projections of the future. So basically what this does is it's answering the question, why? Why are things happening? Why is the temperature what it is? Why is there's so much ice in Antarctica, for example? Such questions is what we're trying to answer through scientific climatology. And then the last part of this is the applied climatology. So basically this addresses the climate factors involved in a broad range of problems related to the planning, design, operations, and other decision-making activities of climate-sensitive sectors of modern society. So basically, what we are doing in applied climatology is answer the question saying, how can we adjust, mitigate, or control what's happening in our climate, or what's happening in the world around us? So for example, if temperatures are changing, then how can we control this temperature change so that it doesn't have too many bad effects on our lives? So what is happening in the climate system? What are the risks and what can be done? That's basically what applied climatology is trying to answer. And the reason why we need to do this is because everything is connected. So this really nice little graphic made by WWF talks about the interactions or the feedbacks between the climate system and people. Because we are not just living by ourselves. So we are interacting with nature. Nature is getting affected by climate change and is affecting climate change. And that comes back as a feedback to us. We know human activities are driving climate change, mainly because by now the main drivers of climate change are greenhouse gases. So as a result of the activities we are doing, we are increasing the greenhouse, and that's climate change. But as I said, the manifestations of climate change are in lots of different ways, and basically can end up affecting us through a feedback cycle. But so as climate scientists, this is what we are trying to do. The question, of course, is how we are doing it. Now, I'm not an applied climate scientist. I am more of a descriptive and scientific climatology person. So basically, this is what I will talk about a little bit. But keep in mind that applied climatology is a huge field. It includes a lot of social activity, it includes a lot of policy decisions, etc. And that is something that lots of people are focusing on. So if that is what drives you, then it is something you can contribute to directly. But what I will talk about is more from the physical sciences side of things. But within descriptive climatology and scientific climatology, we essentially segregate ourselves into two different types of people. They are observation scientists and modelers. Observation scientists are the ones who focus more on the first part, which is descriptive climatology, and the modelers contribute more towards the second part, which is the scientific climatology, because they're converting the observations into a computer code, which can help understand what's happening in the system itself. Of course, observation scientists also do a lot of work on processes, so they do contribute to scientific climatology. And keep in mind that these two groups of people are not working separately, but they have a lot of overlap, mainly because the modelers depend a lot on the observations, and observations are useful only if we can make sense of it. So they depend on the modelers itself. But depending on your interest, you can contribute to any group. So let's talk about observations. What kind of observations are people doing? For example, the easiest one that everybody must know about are these MET stations, which is meteorological stations. And what these stations do is give us measurements of very simple physical parameters, such as temperature, pressure, humidity, the amount of rainfall, etc. And the plot on the right shows the different locations of all these rain gauges and MET stations around India. And as you can see, we have hundreds of them. All of these stations stations have been installed by IMD, and there are a few private met stations also. All of this data is helping contribute to the first problem, which is descriptive climatology, because it gets the state of the atmosphere. Knowing the state of the atmosphere is extremely critical to but also be able to predict into the future itself. So that's one type of observation that is done. The other type of observations are using satellite observations. So satellites are really useful because they can give us geographical information, and they can give us information over long periods of time. So this shows an image from the INSAT satellite, and it's basically showing you the cloud cover. Now this is very useful, not just to know when and how rainfall is going to occur, but also can be used for validating the models which are trying to reproduce clouds. So you'll know by comparison with the data like this whether your models are doing well or not. Another observation are these radars which have been installed by IMD, which give us an idea on not just the type of droplets, the different sizes, etc., but also on winds, etc., which are very useful for constraining the models. So all of this information is inputted into the model itself. So these are the kind of observations that we talk about. But climate sciences, as I said, is very broad. So it's not just talking about the physical state of the atmosphere, but we also worry about things like air quality, etc. So one of the things which has been started by the Ministry of Earth Sciences is this network called SUFFER, which is the System of Air Quality and Weather Forecasting and Research. And what we do is we measure air pollution, mainly because air pollution itself not only affects health and all, but can also end up impacting our climate projections. So for example, all these particles that we keep hearing about in Delhi, the PM 2.5, PM 10, everybody keeps talking about them, mainly because it is extremely injurious to health. But these particulate matters can change the radiation balance of the atmosphere, and hence can also affect how things are happening in the atmosphere itself now. So for example, this is one of the measurements that is done. Sorry. Okay. But so what kind of information can it give us? So for example, these are observations which were done during the Commonwealth Games, which happened in Delhi in 2010. And basically, these straight lines show the period of the Commonwealth. And especially people in Delhi will remember that during the games, there was a lot of talk about air pollution and how it's going to affect the players and athletes. And so a lot of different measures were taken to reduce the pollution. But having these observations is really useful to know whether any of these measures that we are taking have an impact or not. So for example, what we can see is in Delhi University, for example, during the period of the Commonwealth Games, there was actually more pollution in terms of ozone as compared to after the campaign. So after the games, and in fact, this was seen pretty much through all the different measurement sites. In terms of particulate matters, also there wasn't a distinct reduction. If anything, there was a small increase during the games itself. So although these policy decisions were taken, observations are basically what help us to know whether these policy decisions had an effect or were they misguided policy decisions, so that they can be better made in the future itself. So this is where observations can play a very critical role in understanding what is happening. Another thing is if we want to check the impact of vegetation and the impact of anthropogenic emissions, satellite observations like these can be extremely useful. So these are observations of a species called formaldehyde and NO2 over India the different months as measured by the OMI satellite, the Ozone Monitoring Instrument satellite. And what it shows is there is very strong difference in the distribution of the two species across the country. And this helps us understand where do we have, because formaldehyde has a stronger biogenic signal and NO2 has a very strong anthropogenic signal. That this ends up helping us understand what is happening in the world in terms of in the country, in terms of where do we have more biogenic emissions as compared to where do we have more anthropogenic emissions, because then this will help us control the emissions in the future if we want to try and have policy decisions to control pollution. So these kind of observations can be extremely useful for doing that. The kind of observations we tend to do is go to extremely remote environments and make observations of different parameters over there. So this picture on the right-hand side shows the Bharti station. This is the second Indian Antarctic base, which is functional at the moment. The nodal agency which runs this is called the National Center for Polar and Ocean Research, and basically it's run by the Ministry of Earth Sciences. We have a permanent base over there so that we can make observations of different types of things over there to know what's happening in the Antarctic, because what happens in the Antarctic can end up affecting life in India. And it's not just making simple met observations, etc. Sometimes we have to go and measure things in the lake. So this is a picture that I took when I was down there, and you can see climate scientists end up being very outdoorsy, especially if you're in the observing field, because you actually have to go into very remote environments and make observations of different types of gases. So if you are a student who wants to get into observational part of climate change, know that you will get a chance to visit these places which are very exciting but highly dangerous also. Then moving on to that, in addition to making observations in remote places like the Antarctic, we have to remember that most of the Earth's surface is actually covered by the oceans. So what we need to do is go in on ships in the middle of the ocean, stay away from land for days together, and make observations of different parameters over there, because those observations are very critical for modeling, as I'll show you later. So for doing this, it is very typical for these research cruises to happen. This is on the Indian scientific expedition to the Southern Ocean, where a team from India goes from India all the way down to coastal Antarctica and back every single, well, not every single year, every 2 years. And on the ship, we make observations of different things. For example, this is it's a balloon sonde. What it does is it gives us vertical profiles of temperature, pressure, humidity, etc., from the surface of the ocean all the way up into the stratosphere. So these kind of balloons are launched to get the state of the atmosphere again. But it's not just the atmosphere that's important, because the atmosphere is interacting with the ocean. So what tends to happen is we also tend to make observations in the ocean. And for that, we use these instruments. This is a rosette with a CTD. It gives us the temperature profiles from the surface of the ocean down to the bottom of the ocean itself. And all of these observations finally feed into climate models. Again, I'm making this point for the second time. As an observational climate scientist, you will end up going to places like these to make observations in very remote environments. So keep that in mind if you want to do that. Of course, it can be very exciting. So this is a video. Sorry. I don't know why it's refusing to play this. But yeah, this is a video. Okay, yeah, so this is a video of the ship that goes down to the coastal Antarctic, as I said. So as you can see, the environment that we go to is pretty treacherous. We go in places where there is a lot of sea ice, and you have to navigate the ship through waters like these to make observations. But these observations can be very critical in terms of helping understand what's happening in the climate, because the models need observations for validation and also as an initial state, so the model can start from there. So you'll get to see places like these. The kind of observations we make are different. Quick observations through balloon or instruments, and just observations. In addition to making observations on the water, of the water, we also need to know what's happening in the past. So for that, what we tend to do is we end up getting these sediment samples from the bottom of the ocean, because these sediments end up having some information of the climate of the past itself. So getting these sediments and then analyzing in these sediments can let you know how the temperature was, say, 100,000 years ago, or what the acidity was 100,000 years ago, because all these things help us understand how the climate has been evolving. And once we understand that, then we can try and quantify the processes and how things are going to change in the future itself. So that's in terms of making in situ observations in person. But as you can imagine, we cannot go and make these cruise observations every single day. It's very expensive and it's pretty difficult. So there is an attempt to observations as much as possible. On the right, what you see is the the deployment of an Argo float. An Argo is basically the Array for Real-Time Geostrophic Oceanography. And what it is it's an automated probe which is let out into the ocean, and it floats around for days and years together. And what it does is it makes observations of things like the sea surface temperature, the temperature of the water. It will make measurements of the salinity, etc., which are very good markers of climate change, because any change in these parameters will let you know whether the climate is changing or not. And these floats, they go out into the ocean for 3 years. They are there, and what they do is they make vertical profile observations. So they'll start on the surface, go down to about 2 kilometers, and while going down, they'll keep measuring. While coming up, they'll keep measuring. And then once every few days, they will come to the top of the ocean on the surface, and then basically transmit all of their data to satellites. And from satellites, we gather it into our own servers. So what that helps is, as you can see, through all these floats, which have been launched by people all over the world. In fact, India is pretty active in this. INCOIS, which is based in Hyderabad, they have been launching several floats. As you can see, the pink dots in the Indian Ocean are mainly floats launched by India, and that has really changed our understanding of the Indian Ocean itself and its effect on climate, or climate's effect on the Indian Ocean. So these kind of observations can be pretty useful and are becoming more and more common from now. In addition to the observation side, now I'm going to talk a little bit about modeling, because once we have these observations, what do we do? We basically put them into a computer model, and then we try and come up with numbers what's going to happen. And it's a joke within the atmospheric sciences and climate change community that most numbers are made up. And in fact, I guess that's why we have so many climate skeptics, because they don't believe these numbers. But the reality is it's not anything like that. We actually know quite a lot about what's happening in the climate. So what is modeling? When I talk about modeling, it's obviously not doing a catwalk. The modeling is trying to use computers to understand what's happening in the future climate, right? And to understand the processes. So if I ask us a very simple question like this, which was asked by Sergio in 2011, saying that, is a cow more aerodynamic than a car? How will you be able to find that out as a modeler? Obviously, what you can do is you can go take a cow, put it into a wind tunnel, and measure the aerodynamic nature of the cow, as you can do with the car. But I'm sure you must agree that it's pretty hard to get a cow to go into a wind tunnel and stand there while you make your observations. So what you can do is you can use modeling, and you can basically reproduce a cow in your computer code, and then see how the winds move around that. So modeling is basically just doing that. It's a process by which we simulate the composition of the atmosphere and its change, its perturbation because of human activity. And we study the implications of this change on climate and life on Earth. So basically what we have is a collection of ideas which is put into a computer. And of course, it's not very simple, as you can imagine, because there are lots of different processes which are happening. Like a very simple box like this also would have sources from different types of, emissions from different types of sources. You would end up getting deposition from the atmosphere onto the surface. There's and air going out of the box, and there's chemistry happening within the box in the atmosphere itself. And of course, there's exchange happening from the top, and there's solar radiation coming in. So as you can see, we need to be able to account for all of these things to get a good idea of what's happening in the box itself. So a model is nothing but a collection of ideas converted into computer code, which can help solve it. And how do we do that? So let's take a very simple example over here. This is the reaction of nitrous oxide, which makes NO2 and depletes ozone while it's doing it. And through measurements in the lab, so through observations, we know the rate constant for this. And that can be changed into a rate of change of NO, for example. Right, so this is fairly straightforward. All of us have learned this in our 11th, 12th, and undergrad if you have done chemistry. But basically, it's a very simple process. Now, a computer model, what it does, it basically just takes this and turns it into a computer code. So if we want to know what is going to happen at NO at time I, what we need is the concentration of NO at time I minus 1, so the earlier time period, and then the rate of change of NO, which we have computed using the reaction rate constant. So basically what this helps is using the observations, we can always predict what's going to happen in the future. Right, and this is shown for chemistry, but even for physics there are similar equations, etc. So model is nothing but a collection of equations that we solve for time. So if we know what is the state of the atmosphere right now, which is why all these observations are extremely important, and we understand the process, which is the second part of the equation over here, then we will be able to predict what's going to happen in the future. So computer modeling is basically just trying to predict the future, knowing the present and the processes involved. And obviously, it's not as simple as this. There's hundreds and thousands of equations over there. There's physics, biology, chemistry, all of them are converted into computer code. And then we try and try and see what's happening in the future. And why is modeling so important in climate sciences? You can use it as a diagnostic tool and as a prognostic tool. So diagnostic tool is basically to understand what's happening in your climate system. So the process studies, if you are able to model it, you understand it. That's how you approach it, right? So they can be used to understand the process itself. We can do comparisons of the model and data to know whether our current understanding is correct or not. So for example, if your model is completely wrong, then you know there's some process which is not characterized properly or missing in your model. So you need to improve your model. And also we can start looking at bigger pictures. So for example, if I make observations of pollution in Delhi only at 7 different measurement locations, then do we know what's going to happen in the rest of Delhi? Yes, we can use a model to try and increase the scale and understand what's going to happen in each and every region of Delhi rather than only in places where we have air pollution observations. So things like that, models can be very useful. And also we can understand what's happening to the species also. So for example, I showed you an equation of ozone before. So to know whether ozone is increasing or decreasing and what is it increasing or decreasing because of, those kind of questions can be answered using models. But the main reason why we are trying to do all of this is to use these models as prognostic tools, which is basically to predict what is going to happen in the future. Because the only way we can make informed policy decisions is if we have confidence in our future predictions. So if we can predict what's going to happen in the future, for example, even something as simple as weather prediction, then we'll have confidence saying that if the weather prediction is correct, maybe we need to take some action about whatever weather event is under consideration. So we can use it for prediction. And also these models, once we can see that it is reproducing our climate system well, we can also do... Sorry? Okay, I think there's somebody's interference over there. If you can please mute your microphones, that would be useful. But yeah, so once we have confidence in our models, then we can actually start answering questions of what if. So for example, what if the CO2 concentration increases by a factor of 2? What kind of impact is it going to have? These kind of questions can be used. These kind of questions can be answered only using models, because we don't have another Earth to go and make these experiments and see what's going to happen over there. So models can be very useful as prognostic tools to see what's going to happen in the future. And in fact, we do see that one of the things which has increased in quality over the last 2 decades, especially over India, is the rainfall prediction. It used to be a very common joke, and in fact, people even crack it right now, saying that if the IMD gives you a weather prediction, you should do completely opposite to what they have predicted. So for example, if it's going to rain, don't carry an umbrella. If it's not going to rain, then carry an umbrella. Was the joke which used to go around. But now the weather prediction, it has improved exceptionally. And the reason why it has improved exceptionally is, first, there's a lot more observational data. And plus the second thing, we have improved our computer models. So these models can really reproduce the state of the atmosphere. And we can see that very clearly in, for example, right now there's a cyclone going on, and we are getting perfect predictions for that because our computer models are doing so much better than they used to do in the past. And the reason for that is, in the past, at least until the early 90s, we used to use statistical methods of prediction. So for example, in the last 10 years, on 10th of July, there was so much rainfall. So the most likely, there was an X amount of rainfall. So the most likely amount of rainfall right now is also X. That's how statistical prediction works. But now in our computer models, actually put in the physics, we have put in the chemistry, we have put in the biology, and that has really helped the weather prediction itself. So this is the prediction. It is actually for now, 26th of May was the initial condition, and then this is a prediction for the next few days going into June. And as you can see, there's a lot of rainfall which is coming because obviously we are heading into the monsoon season. And the reason why we have confidence in these predictions is because we've validated them against observations in the past, and they have been correct, and hence we have confidence that it's doing well in the future also. But why is it improving? So this is the main reason why we are seeing a lot more confidence in our projections of the future. And that's because the climate models are really developed. So in the mid-70s, the earliest models were basically only the atmosphere, right? We basically just had the atmosphere in terms of the temperature, winds, etc. in there, because obviously the computational power was very low. Then in the mid-80s, land surface and atmosphere interaction was integrated into the model, and then ocean and sea ice was started getting developed. In the 90s, ocean and sea ice went into these big models. And as you can see, the complexity kept on increasing as we went ahead. So much so that today, the climate models we use are not just a simple atmosphere land surface model. They in fact include everything from the atmosphere to dynamic vegetation, atmospheric chemistry, etc. So because it's such a complex system and everything interacts with each other, unless you are able to put all of these terms into your model, your predictions are not going to be accurate. And increasing the complexity increases the accuracy of the models itself. So this is where we are today. And as you can see, all of these things need a different type of scientist. Some need chemistry, some needs biology, some need physicists. So basically, no matter what your background, you will be able to contribute to climate sciences if you're interested in this field itself. And this is basically what has increased our confidence. And because of that, we can act on it. So a simple thing is, in 1999, there was this huge cyclone in the Bay of Bengal. It was called BOB 06, and it hit Odisha. And about 10,000 people had died during that point. Now, the reason for this was obviously it was a pretty severe cyclone, but also in addition to the severity of the cyclone, what happened was there was very little action taken by the country, by the state, in terms of evacuation of people, etc. And that's mainly because, first of all, we did not have that much of an understanding. And the second thing, the prediction was not extremely accurate. So we did not know exactly where it was going to hit. And so you could not take policy decisions to evacuate, lakhs of people without knowing exactly where it's going to hit. But in 2000, we had the cyclone Fani. This was also a massive cyclone. In fact, it was bigger than the BOB 06 cyclone. But the number of people who died over there was less than 100. And you can immediately see that there's a huge difference that happened. And why did this happen? Is because our prediction system was so much more accurate in 2019 as compared to 1999. And because it was so accurate, our policymakers, our politicians, our bureaucrats, they had confidence in our predictions. And because they had confidence in our predictions, they were able to take action and evacuate people at the exact location where the impacts of the cyclone were the harshest. So as you can see, getting your models right, improving your models, improving the complexity, improves the accuracy, and that has direct implications in terms of life. So to end with, what are we going to talk about? We're going to talk about who can work in this field, because as I said, it's really broad. And a simple answer to that is almost everyone can work in climate sciences in one way or another, right? So, no matter your background, whether it's basic sciences, whether it's engineering or not, whether it's social sciences, you can contribute to climate sciences work. The kind of work that happens is, first of all, there's obviously a lot of research. And in terms of research, there are both governmental and private institutions involved. Obviously, the big money is with the government, because the government is trying to understand what's happening in the future as compared to private. Also changing because now things like insurance companies, etc., have understood that the payouts they will pay will be really large unless they're able to accurately predict what's going to happen in the future. So a lot of private money is now coming into climate research. Of course, there's a lot of social work, mainly because all of climate change manifestations are in terms of impacts on humans and the ecology. And because of that, obviously, there's a big social sector which is involved in it, and that's from the government, from the private sector, and from NGOs, etc. And because it's impacting people directly, there's always going to be some activism involved, where people are starting to wake up and starting to question their own government, saying that, hey, climate change is happening. What are you guys doing about it? So there's a lot of different ways in which you can contribute if you are interested in climate sciences. In terms of where all can you work, basically I made a list of some of the places which, and this is definitely not an exhaustive list, but in India, most of the climate sciences work is happening through the two ministries, which is Ministry of Earth Sciences and Ministry of Environment, Forest and Climate Change, MOEFCC. And to that, pretty much all the large universities now have a program on either atmospheric, oceanic, or environmental sciences, or even on climate change itself. So if you want to go ahead and study or work in this field, there's lots of different organizations which you can go and start working at. In addition to that, there are lots of private organizations. I've just listed three here, which are extremely active: the Center for Environment Education, WWF obviously, and WRI, which are doing quite a lot of work in India itself. And if you have any specific questions about your own background and how you would like to approach this field, I'm more than happy to answer this. I should mention that in addition to these ministries, we have all our other ministries, including DST, etc., which fund a lot of projects which work on climate change. In fact, even if it is not directly trying to measure things in the atmosphere, we have programs. For example, the chair of INEAS, he's got a pretty large grant, which is to try and work on carbon on carbon sequestration and on batteries. And these things are indirectly related to climate change itself. So lots of different ways in which you can contribute to climate change. What I would say is, if you have aptitude in something, you pursue that, and there will be a linkage you can find to climate sciences through your own area of research itself. With that, I'm going to stop, and I'm happy to answer any questions that you have. So I'll stop sharing my screen and start my video.
Yeah.
Virendra, will you be asking questions?
Yeah, thank you very much, Dr. Mahajan, for a very interesting talk. So in chat of
Sure.
course, I could see some of the questions are there. So let me pass on these questions to you.
Okay.
Oh, many questions are there. So first question is the Kamal Divedi. She want to know how to proceed ahead with further study in this field.
Right. So there's no simple answer to this, mainly because, as I said, it's so broad. What I would say is, think about what you have done your undergraduate in, or you have done your 12th standard in, and where your aptitude lies. So for example, I am a chemist. I did not study climate change, but I studied chemistry. And then through chemistry, I went ahead and started doing atmospheric chemistry, which is related to climate change. So whichever subject you are studying, you can follow the same subject ahead and find a project which links to climate change. That's one option. The second option is, as I said, lots of universities now offer a formal course in atmospheric, oceanic, or climate sciences. So there are universities which have a course, and you can go ahead and apply to those. Plenty of universities within India do that, and of course internationally also there's quite a few universities. Even the ISERs, which are some of the top organizations in the country right now for basic sciences, some of the ISERs have already got a course in climate sciences. So ISERs are another option. Even premier institutes like ISC in Bangalore, it has a course on atmospheric sciences. In fact, it has a very strong department on climate, ocean, and atmospheric sciences. So there are various ways in which you can approach it, but my suggestion is always follow the subject that you're good at, because the best way you can contribute is contributing through what you're best at.
Thank you, Dr. Mahajan. The another question is from from Ankit. It's I am learning mathematical modeling and simulation. How to start with climate science?
Right. So Ankit, it's a very good question. See, so one of the things which is true is we really need good programmers. Right now, the climate modeling community is in need of very talented programmers. So if you're already starting to do mathematical modeling and simulation, that's a perfect start. How do you start with climate sciences? It depends on what level you are. If you want to start working on large climate models, then there are some models which are publicly available. So for example, you have the WRF-Chem model, which is a weather forecasting, but can be used for climate forecasting also. Or you have the CAM-Chem model, which is a community model. So you can always access that. But keep in mind, because of the complexity of these models, you will invariably need access to a very high performance computing system. So it's not that you can do climate modeling from home anymore. That used to be true years ago, but now because of the complexity of the models, you need very high performance computing systems. So for example, the Center for Climate Change Research in Iitm, the institute that I am in, has developed the first Earth system model from India. And so if you are interested in this, get in touch with these centers which are running these climate models, and they will be the best to help you get into a project related to climate modeling itself. But yes, you definitely need to have a background either in mathematics, physics, or programming, because most modeling needs that. I'm not saying biologists do not contribute to climate modeling, because the process is again necessary, but coding and programming is a basic need for any kind of climate and mathematical modeling.
Thank you, Dr. Maharaj. Projects or some internship can guide about it.
Yeah, so most institutions tend to have internship programs now. I can give you an example from my own institution. We have internships which range from a month to a proper master's project or like a PhD project itself. So there's a whole range of options over there. Most researchers that I have interacted with are pretty happy to have interns. The only thing is, one thing I've noticed is because obviously the COVID situation and all, right now you cannot do internships in terms of field work, but what you can definitely do is internships in terms of data analysis and modeling. So the best way to approach internships is to identify a potential guide and then approach them. And you can literally, any professor in climate sciences, if you write to them, you will get some kind of a feedback saying whether they can or cannot do it. The other way is institutions have formal internship programs which get advertised at the start or end of academic years. And if you go through their websites, you will see there is always an option for careers or internships, and you can apply through that also. So there are different ways, but my suggestion is always identify a person to work with, because that really makes things easier.
Thank you, Dr. Mahajan. One question from Follow Me. What are the good postdoc and RA opportunities for climate science in India?
Okay, so in terms of postdocs and RAs, I don't think it is very different from any other subject. Most of the universities, etc., have their own procedure for doing postdocs and RAs. So you have to go through the same procedure. In terms of the ministerial research centers, for example, Iitm in Pune or NCPR in Goa, etc., they also advertise postdoc and RA positions every year without fail. And then you have to go through an an interview process and then finally get selected. There are lots of opportunities about this. It's not as if there is a dearth of positions. It's just finding the right position is important, of course, because that's going to determine where you're going to go. Besides that, of course, out of India, there are plenty of options that you can apply to, but it's not that you have to go out of India to do good science in climate sciences anymore. In India, there are plenty of good organizations. And as I said, there are researchers in not just the ministry-run institutions, but also the more independent institutions like ISER, etc., which have postdoc and RA positions. So again, identify the subject area, because at that level, you should have narrowed down a little bit more in terms of what kind of climate sciences you want to work on. Identify the subject area and write to researchers. That's probably the best way to to find out whether there are positions or not. And as with the earlier internships questions, all these institutions do have a career and vacancies page, and get advertisements over there for these positions.
Dr. Mahajan, do you have any internship opportunity for master students at IITM?
Yeah, so in Iitm also we follow, there are two types of internships. For 1 or 2 months, we tend to get students quite often. And then we have the longer term internships. For the longer term internships, we have the official procedure, which is advertised on our website, which is tropmet.res.in. And if you go on there, there's a link where you can go and look at what are the possible positions, and you can apply through that. If it is a short-term internship, then you can write not just to me, but other researchers also within IITM, and that is a personal conversation to be had, because short-term internships, in order to make them very productive, the fit needs to be right. So you really need to talk to researchers about that. But yes, there are opportunities for master students at IITM. There are opportunities for people who just want to do a short-term internship. There are opportunities for people who want to do PhDs. The PhDs are with fellowship also. So if you get through the interview process and you're selected, you will get a stipend on top of that. For masters, we do not offer a stipend, but we do offer the internships itself.
One question from Shubham Kumar, that Jharia coal field in Jharkhand, the pollution in environment is increasing day by day. So how do we can make awareness to?
Yeah, so that's a very good question. See, I'm a very big advocate of working with the government, because the large changes are always brought by the government itself. So the best way to even answer this question about the coal field in Jharkhand is to talk to your local representatives. So your MLAs, MPs from your region. Those are the people you need to approach, because the more they get the feedback from people, the more willing they will be to change. So it's a misnomer, or it's a misunderstanding that politicians don't listen to us. Politicians always listen to their populace, but not enough people are reaching out to them saying that this is a problem. So, for example, if you're talking about this coal field in Jharkhand, we know coal is a big issue, but we have to balance our energy requirements as compared to pollution. All those reality are there. But if tomorrow 200,000, 300,000 people from Jharkhand write to the local MLA saying that we don't want this here, action will be taken. So talk to your local representatives. You have to approach the government.
He's asking any technological way by which we can also work on energy requirement from coal.
Yeah, so in terms of clean technology, that's one of the things I haven't touched upon, because I don't work that on this, but that's in the last of the three broad segregations, the applied climatology. Technological solutions do exist. Some of them are expensive, some of them are cheap. So there's obviously going to be an economic balance that has to be reached over there. But yes, I mean, for example, right now, Norway, was it Norway or Finland? They have one of the cleanest coal plants in the world. In fact, their emissions from the coal plants are basically just carbon dioxide, which comes out with hardly any other pollutants which affect human health directly. So the technological solutions are there, but they can be expensive. But it's not as if the technology is not there anymore. Right now, at least in climate sciences, we do have enough information and we do have enough technology to solve most of the questions, but the political will needs to develop further. And that's going to happen as people become more aware and they start asking the elected representatives to take action.
Yeah, thank you, Dr. Mahajan. I think I have covered most of the questions. Yeah, looks like.
Excellent. Okay.
So
Yeah, I see that somebody is also. Sorry, I see that somebody has made a list of possible institutions, and that's great. Prasad, I completely agree. There are not just these, but several other institutions which have good centers working on climate change. But yeah. So basically, look around. Search a little bit more, and you will definitely find an institution within your region that is working on climate change.
So Vivek, if you have any question from YouTube.
No, there is nothing from YouTube.
Okay. So thank you, Dr. Mahajan, for very interesting stuff. I really like it. I really enjoy it. Thank you very much.
Thank you, and thank you for having me on the platform. It was really nice to talk about our subject matters from a broader perspective, and hopefully